All right, today we're going to work with how to factor a difference of two squares, and we should probably talk about what the word factor means first. If I want to factor something like 27, if I want to factor the number 27, I say what times what makes 27? Wouldn't that be 9 times 3? 9 times 3 makes 27. So this right here is what we call factoring something. When we break it down into something times something makes the original. So if we go back to what we've been doing with a difference of two squares, if I tell you to factor x squared minus 25, what we're doing is we're going backwards into what times what makes this. Well, what we learned is that when I had an x and I had a plus and a minus, and what do I multiply by itself to get 25? 5, right? When I have two binomials that are exactly the same, but one of them is a plus and the other one's a minus, then I always get this right here. Well, guess what? Right here's your answer. We have now factored x squared minus 25. In other words, we're just going backwards. All right? So this is why your root sheets will come in handy. So let's do another problem. What if we had a squared minus b squared? A squared minus b squared, this is as easy as we think it is. This just factors into a plus b times a minus b. That problem is done. It has been factored, all because of the difference of two squares shortcut. If I were to try to do FOIL with this, I would get this. All right, but we don't have to because we know the shortcut. Easy enough? Now, of course, there's some things that we need to know about this. Number one, if it's not a difference of two squares, if it's a sum of two squares, we don't have a rule for that. So this one won't factor. All right, if you see a sum of two squares, we can't do this. All right. I already talked about using other letters, but you could have some that have numbers with it as well, like 4x squared minus 49. First thing we ask is, are both of those terms perfect squares? And they are. They're both perfect squares, so my first step is to set up my two sets of parentheses. I know that I'm going to have a plus and a minus, and then I just think, what is the square root of 4x squared? 2x. So I put that 2x there and there, and I put the 7 here and here. Easy enough? All right? Now, so the process is always the same. Now, there's one other thing I need to show you that I think you could run into, maybe not in tonight's homework, but maybe in tomorrow's. If you see one like this, 8x squared minus 50. If you look at those two terms, those are not perfect squares. They're not perfect squares yet. I could think distributive property backwards. Does everybody see that there's a 2 in both of these? Isn't 2 times 4, 8? And 2 times 25, 50? So I can factor out a 2, thinking like backwards distributive property. And what I have now is 4x squared minus 25 in here. If you think of the way distributive property works, if I distributed this 2 through, I would get this. All right? So that should make sense to us. Now, look what I have now. Now what I have is a difference of two squares. So we can factor this into 2x plus 5 times 2x minus 5. I just need to stick this little 2 out in front of it. That doesn't happen very often, but I think you will see it on tomorrow's assignment, and we just need to be aware of it. All right? One other thing. This is a great time for us to introduce our new function family member, and that's quadratics. Quadratics are functions that have an x squared in them. And we're going to expand this idea in the next couple of weeks. But some of the ones we've looked at today, these are quadratics. If I see x squared minus 25, that is a quadratic function. And that quadratic function also has a graph with it. The graph of that quadratic function looks like this. It's kind of a U-shaped, rounded curve, and it actually has a name. The name of that graph is not a line. The name of it is, it's called a parabola. That's the name of that graph. The graph of a quadratic function is always a parabola. And here's the cool thing. This is why I decided to do it this way today. We can find the intercepts, the x-intercepts of this, using what we did today. When we found the x-intercepts, when we did linears, we always set the y equal to 0. Well, in this function up here, this f of x is like a y. We've said that before. So let's replace it with 0. If I solve that little equation right there, it will tell me where the x-intercepts are. And guess what? From what I just taught you today, this is easy to solve. This thing will factor into x plus 5 times x minus 5. That's what I just taught you a minute ago about the difference of two squares. And there's a rule in math called the zero product property that says now I can set each of these little binomials equal to 0 individually. And I think you can agree those are very easy algebra equations to solve. All right? Over here I would add 5 to both sides. X equals 5. Over here I would subtract 5 from both sides. So x equals negative 5. And those two numbers tell me what the intercepts are over here. One of the intercepts is positive 5. The other intercept is negative 5. How cool is that? All right. So tonight I'm going to have you solve a few of those like that. It just means that once I get it factored right here, I need to keep going and set each of those pieces equal to 0 and solve them. All right? But most of what you're going to be doing today is just taking a very basic difference of two squares, like x squared minus 81, and factoring it into x plus 9 times x minus 9. That's a lot of what you're going to be doing in your assignment today. And we will stop there for today.